Hello students, my name is Priyanshu Malik from BSC Chemistry Honours, the final year. Today we are here to discuss the phase rule. This video is for visually impaired students. Let's start with the physical chemistry. And the topic is a phase rule, and we start with the explanation of Gibbs phase rule. Gibbs phase rule cannot be expressed in what is described by mathematical equation as under. For a heterogeneous system in equilibrium where f is equal to c minus p plus 2, f is equal to number of degrees of freedom, c is equal to number of components, p is equal to number of phases. Next topic will be about the phase component degree of freedom. A phase may be defined as the part of system which is homogeneous and separated from other parts of the system by distinct boundaries, physically and chemically different from the other parts of the same system, and mechanically separable from other parts of the system. Some examples are given below, such as ice and water, which has two phases, one solid and liquid, water and water vapor, two phases, one liquid and one gaseous, ice, water and water vapor, three phases, one solid, one liquid and one gas, two miscible liquids that water and alcohol, three phases, two solid and one gaseous. Miscible gas and miscible liquid constitute a single phase. Solid plus liquid, solid plus gas, liquid plus gas, two solid and two immiscible liquids constitute two phases. Different colloid, different solids are regarded as different phases. However, intimately they may be mixed components. The number of components of a systematic equilibrium is defined as the smallest number of independently variable constituents by the means which the composition of each phase present can be expressed either directly or in the form of chemical equation. Negative and zero signs paper. Example: water system consists of the equilibrium ice, water, vapor. This system consists of one component only, that it is a one component because the composition of each of the three phases present can be directly expressed as H2O. Sulfur system. Sulfur consists of four phases: monoclinic, rhombic, liquid, and vapors. It is also one component system because the composition of each phase can be expressed in the term of constituent. Sulfur decomposition of calcium carbonate by heat can be expressed according to equilibrium. Calcium carbonate, calcium oxide plus CO2 carbon dioxide. Thus, they are three different constituents forming three different phases, but the composition of each phase can be explained in terms of any of two constituents. For the example, if constituent fusions are for example, the constitution are calcium oxide and the carbon dioxide in the phase calcium carbonate is equal to calcium CaO plus CO2, CaO is equal to CaO, 0 CO2, CO2 is equal to 0 CO, CO2. The constitution are calcium carbonate and carbon dioxide and then phase composition. Calcium carbonate is calcium carbonate plus 0 CO2. Calcium oxide is calcium carbonate minus CO2. Calcium oxide is equal to 0 CO plus CO2. Similarly, composition theories can be explained in terms of calcium carbonate and calcium. Thus, the dissociation of calcium carbonate is a two-component system. Sodium sulfate water system. Such a systematic equilibrium contains a number of phases like Na2SO4 10H2O, Na2SO4 7H2, Na2SO4 solution, ice, water, and vapor. But the composition each phase can be expressed chemically terms only in hydrosodium sulfate Na2SO4 and water H2 phase composition Na2SO4 10H2 Na2SO4 Na2SO plus 7H2 Na2SO4 plus 7H2 Na2SO4 Na2SO4 plus 0H2 Na2SO4 solution X Na2SO4 plus YH2O ice and 0 Na2SO4 plus H2O Na2SO4 water 0 Na2SO4 plus H2O vapor 0 Na2SO4 plus H2O. Thus, the smallest number of independent variables constituted by which the composition of the phase present at equilibrium can be expressed is 2, and Na2SO4 and H2O, and it is also a two-component system. Degree freedom variance. Degree of freedom variance of the system is the smallest number of variables affecting the temperature, pressure, and concentration of the component, which must be arbitrarily fixed in order that heat conditions of the system may be completely defined. Examples are ice, water, vapor system. In this system, there are three phases of one component H2. The three phases can coexist in equilibrium only at one particular temperature and under one particular pressure, and variation of this factor will lead to the ultimate disappearance of one or more of the phases and therefore destroy the system. And this system has no degree of freedom is invariant. The same result follows the phase rule that F is equal to C minus P plus 2. 1 minus 3 plus 2 is equal to 0. Water vapor system. The system consists of two phases of one component as the vapor pressure of the water is definite at definite temperature, indefinite of the amount of water present. It follows the temperature is fixed. The vapor pressure is also fixed, and conversely fixing the pressure fixes the temperature. Thus the system has only one degree of freedom. In other words, it is univariant. For a gas, the temperature, pressure and the concentration volume are related according to the equation PV is equal to RT. Thus, in order that the system may be completely defined, any two factors out of PVT must fail, hence it follows that a gas has 2 degrees of freedom. Bivariant. But the number of component phase and degree of freedom follow in the equilibrium system. Calcium carbon, calcium oxide plus calcium CO2. Number of components, 2 number of phases, 3 degree of freedom F minus C minus plus 2 square F is 2 minus 3 plus 2. Explain. Let's start with the equilibrium system. In equilibrium, a system is said to be in equilibrium if the property like temperature, composition, pressure, the various phases don't only change with time. A system is said to be in state of full equilibrium if the same state can be achieved by approach from either direction. For example, equilibrium between ice and water at 1 atm pressure and 0 degrees Celsius is a true equilibrium, because it can be attained by the melting or sound freezing of time. If the state of the system can be attained only by one direction, the to be very careful change of condition, it is called as a state of metastable equilibrium. For example, water at minus 2 degrees Celsius can be obtained by very careful cooling of liquid water but not by melting ice. Hence, water at minus 2 degrees Celsius to be in state of metastable equilibrium. Let's deduce the thermodynamic phase rule equation. Consider a heterogeneous system of C components C1, C2, C3 distributed among P phases P1, P2, P3 as shown in the figure. Degree of freedom of a system is equal to the number of independent variables that are deleted before. The system completely clearly the number of these variables is equal to the total number of variables of the system minus the number of variables which are defined to the system itself because of its being in equilibrium. Thus, degree of freedom is total number of variables, maximum number of variables defined by the system because of its being in equilibrium. The total number of variables can be calculated as follows. Suppose a phase contains two components, and if the molar concentration on one component or known, then the other can be calculated by difference. Thus, the phase containing two components can be defined by one concentration. If a phase known be contain three components, to define the component two concentration should be known, because then the concentration third can be defined by difference. Hence, in general, if a phase contains C component can be defined completely by C1 when its concentration terms of variables. To define the system completely at all the P phases, the total number of concentration terms of variable required will be P E C minus 1. Beside this concentration variable, the temperature and pressure of the system, which are the same for all phases, are variables that follows. Then the total number of variables P is equal to C minus 1 plus 2. The number of variables defined by the system itself because of being in equilibrium can be calculated fully. When the system is equilibrium, the chemical potential of the component U mu is the same as normal phase. Thus, if a system consists of three phases, say A, B, and C, then for any component at I, mu I A is equal to mu I B is equal to mu I C. These are two. Why one mu I A is equal to mu I B, and second mu I B is equal to mu I C. Thus, for the system, three phases, two equations are known for each component. Similar for system, four phases, three equations are known for each component. And for a system, P phases, P minus A equation are known for each component. For system B phases, let's start with the uh, water system. The system consists of three phases: ice, water plus vapor. The three single phases may occur in four possible combination equilibrium as liquid vapor, solid vapor, solid, liquid, vapor. The number of phases that can exist in the equilibrium at any point depends upon the condition of the temperature and pressure. These conditions have been determined experimentally, and a phase diagram is obtained by plotting pressure against temperature. The phase diagram consists of three stable curves OA, OB, and OC, and one metastable curve OA hash, three areas, and a definite point O. These are separately discussed at present. Every curve and every point can be seen in this figure, where O is the triple point. We can explain in this by the full diagram by theory. Curves OA. This is the vapor pressure curve of water representing the equilibrium between liquid water and vapor at different temperatures. At any point on the curve, the phases are present. The curve starts from the point O, the freezing point of water, and ends at A. The critical temperature 374 degrees Celsius, beyond which the two phases merge into each other. Consider any point on the curve. Now for a fixed value of pressure, temperature is also fixed value. Hence, if by keeping the pressure constant and time is made to raise the temperature, the liquid phase will disappear and the temperature is lower, then the vapor phase will disappear. Therefore, to define the system completely at a time, it is necessary to mention either temperature or pressure. In other words, pressure being fixed, it is not necessary to mention temperature is automatically fixed. This water vapor system is univariant, it has 1 degree of freedom. It also follows the phase rule equation. F is equal to C minus P plus 2. F is equal to 1 minus 2 plus 2 is equal to 1. OA, the dotted curve OA, a continuation of the curve OA, represents the vapor pressure curve of supercooled water. It is metastable curve. On the slight disturbance, the supercooled phase at once changes to solid ice and curve merges into OB. OB is the sublimation curve or the water vapor curve of ice. It gives various values of temperature and pressure at which ice and vapor can exist together. It is obtained by studying the effect of pressure on the freezing point of water. The curve starts from the point O, freezing point O, and ends B minus 273 degrees Celsius. As temperature decreases, the water pressure on the ice tends to become insignificant. Again, we see that for a particular temperature, there can be only one pressure value and vice versa. In other words, ice vapor system is universal. That is, only has 1 degree of freedom. Curve OC, it is a melting point curve and represent the equilibrium between ice and liquid water at various pressures. In other words, it shows the effect of pressure on the melting point of ice. It should be noted that the line OC is inclined towards the pressure axis. The slope of the curve OC clearly indicates that the melting point of ice is lowered by the increase of pressure. There is, however, no limit for the curve OC. It goes up in the point of corresponding to 2000 atmosphere and minus 20 degrees Celsius. At this point, one type of ice changes into solid modification, but the solid liquid equilibrium still remains. At any point on the curve OC, two phase ice and liquid water are present in equilibrium, hence the system is univariant. Areas. Now we talk about the areas. The areas that the regions bounded by the two lines gives the condition of temperature and pressure under which the single phase that ice or liquid water or vapor is capable of stable existence. Area below AOB has water vapor. Area BOC has ice and area CO has liquid water. These areas are bivalent as located to area BOC as an ice area liquid. This area bivalent located any point in the area. Temperature as well pressure must be fixed, thus indicated 2 degree of freedom. This also follows from the phase rule equation. F is equal to C minus P plus 2. Triple point. It is a point where the three curves OA, OB, OC meet. This point the three phase ice, water and vapor are in equilibrium. It should be noted that it only a point indicated there will be only one set of conditions under which it is possible for the three phases to exist together. The point O is a self-defined point corresponding to definite temperature of 0.0098 degrees Celsius and a definite pressure of 4.58 millimeter. If either pressure or temperature change, then one of the three phases will disappear. Since only changing either pressure or temperature, one of the phases disappear. Therefore, the system at the point O has no degree of freedom. It is invariant. Follow the phase rule equation. That's Explain why the fusion curve of ice has a negative slope, where the sublimation of positive phase of diagram of water. This is because the freezing water point of water is depressed by the increase of pressure, and therefore the fusion curve is inclined towards the pressure axis, that it has negative slope. But the sublimation curve has a positive slope, that inclined away from the pressure axis. This is because the vapor pressure of the water increases with the rise of temperature. Let's discuss sulfur system and its element feature. It is one component system comprising four phases: rhombic sulfur, monoclinic sulfur, liquid sulfur, and the vapor sulfur. This is a typical example of one component system exhibits solid transformation. Sulfur exists in two well-known crystalline forms, namely rhombic sulfur and monoclinic sulfur. The two forms are in equilibrium with each other at 95.5 degrees Celsius, which is a transit temperature defined as the temperature at which one stable form of a solid is transferred to another stable solid form of it without any change in temperature, pressure, the system, or the atmosphere. Rhombic sulfur is stable below 90.5 degrees Celsius. The monoclinic sulfur is temperature. According to the phase rule, the equation all the four phases cannot coexist in equilibrium because of substituting P is equal to 4 and C is equal to 1 in the phase rule equation. We have F is equal to C minus P plus 2, 1 minus 4 plus 2 is equal to minus 1. That we get F is equal to minus 1, which is meaningless. Hence, for a system consists of cell components, it is not possible to have four phases together in equilibrium. However, it is possible to have three or fewer number of phases to exist together. The phase diagram of sulfur system is obtained experimentally by plotting pressure versus temperature as shown in the figure below. The diagram consists of six stable curves BOA, AO, OC, AC, and CF. The four metastable curves OD, OG, AD, and CD. The curves divided the diagram into four areas, that to the left of BOCF, below BOA, to the right FCA, and enclosed by OCA. Areas. The areas are by band because to locate any point in the areas, both temperature and pressure are to be fixed up. Each area represents the condition for the stable existence of single phase. In area, thus there are two degrees of freedom, which also follows from the phase rule equation. F is equal to C minus P plus 2. Putting the value of C is equal to P is equal to 1. We get F is equal to 1 minus 1 plus 2 is equal to 2. In the area to the left of the BOSF, only SR rhombic sulfur exists, while in the areas below BOA only SV sulfur vapor exists. To the right of FCAE, as a liquid sulfur is present in the region enclosed OCS and monoclinic sulfur exists. Now we talk about curves. The first curve we will talk about is OP. OP is the sublimation curve of rhombic sulfur. The two phases present equilibrium along this curve are SR and SV. The curve starts from the point O, the transit temperature of SR and SM, and at P 50 degrees Celsius, below which vapor pressure SR cannot measure. If heating is done rapidly, then it is possible to heat rhombic sulfur above the transit point along OD. OD is the metastable curve, and the slight distance emerges into curve the vapor pressure curve of monoclinic sulfur. That OA, it is the sublimation curve of monoclinic sulfur. The two phases present in equilibrium along this curve are SM and SV. The curve starts from the point A, melting point of S, and that's of transition temperature SR 95 degree 5.5 Celsius. Except the point where the three phases SR, SM, and SV are in equilibrium. At any other point along the curve, only two phases SV and SM are in equilibrium. For a fixed value of temperature, pressure is automatically fixed. The degree of freedom also is 1. If the temperature of monoclinic sulfur is lower than the normal, it will change into rhombic sulfur at 95.5 degrees Celsius. But it is possible to prevent this conversion by cooling. Then we will go along with the curve, which is metastable vapor curve of monoclinic sulfur. Curve AV. Curve AV is the vapor pressure curve of liquid sulfur. The two phases present in equilibrium along this curve are monoclinic from the effect of the pressure on the transition temperature of rhombic. The slope of the curve is away from the vertical, indicating that the transition point is raised by the rise of pressure. The curve ends at the point C, after which monoclinic sulfur is AC is the melting point curve of monoclinic sulfur. It represents the equilibrium between the monoclinic sulfur and the liquid sulfur, and is obtained from the effect of pressure on the melting point of monoclinic sulfur. The curve is inclined away from the pressure axis, showing that the melting point is reached by the rise of pressure. The curve at the C beyond which monoclinic sulfur ceases to exist in a stable condition. The system has degree of freedom equal to 1 CD. This curve represents the equilibrium between rhombic sulfur and the liquid sulfur and is the metastable melting point curve of rhombic sulfur. Since the curves OC and AC meet at C, for which the condition are 155 degree and Celsius and 1290, it follows that if the liquid sulfur were cooled at a pressure higher than 1290 atmosphere, then rhombic sulfur will crystallize at once. No monoclinic sulfur being formed. The curve passes through the point C, and beyond this point becomes a stable melting curve, CB of rhombic sulfur. There are three stable triple points with OA and C in the phase diagram at the point where the phase is in equilibrium of sulfur monoclinic and vapor. If one of the variables is changed, one of the phase disappears. Similarly, A is also on a triple point between monoclinic vapor and liquid sulfur. This point is again invariant for the lines OC and AC intercept C to yield a three-phase equilibrium between rhombic monoclinic liquid sulfur. On changing one of the variables, ether pressure and temperature, one of the four phases disappear. Therefore, the system at the triple point has no degree of freedom. This also for from phase rule equation F is equal to C minus P plus 1, F is equal to 1 minus 3 plus 2 is equal to 0. D is a metastable triple of the phase equilibrium being SRL, SL and SP. Now we discuss about salient feature of lead silver system. The various phases possible are solid lead, solid silver and silver in the molten state and fourth vapor. Since the small changes of pressure have negative effect on the equilibrium existing between the lead and silver in the solid state or in the molten state, we can use the reduced phase equation F hash is equal to C minus P plus 1. According to the equation F hash is equal to 0, P will be 3. The maximum number of phases other than vapor that connects will be 3. The phase diagram of lead silver system is shown the figure next to it. The diagram is taking temperature and composition on the axis. The diagram consists of temperature OA, OP and intersection at point O. Various curves and points are described in the curve OV. It represents freezing point curve of silver to which the successive small quantities of lead are added. The point A indicates the melting point of pure silver 961 degrees Celsius. It is observed that the melting point silver is lowered gradually by the addition of lead into it. Along the curve, the added lead goes into the solution and the separation of silver occurs when the point O is reached. At this point, no more lead goes into solution and the solution becomes saturated with respect to the lead, and hence the melting point of silver does not fall any longer. Thus, the point O represents the lowest possible temperature 300 degrees in the system that corresponds to fixed composition, while 2.4% silver, 97.6% lead. The point O is called eutectic point. All along the curve over two phases, solid silver and liquid melt up as an equilibrium, neglecting the vapor. So therefore the system univariant shown below. F hash equals C minus P plus 1, 2 minus 2 plus 1 is equal to 1. Curve OP in the it represents the freezing point curve led to which the successive small amounts of silver added. The point B represents the melting point of pure lead, 327 degrees Celsius. It is seen that the addition of silver to lead lowers the melting point of lead. All along this curve, the layer which is added goes into the solution while the separation of lead takes place. This state of affairs continues till the point O is reached. At this point, no more silver goes into solution. The solution is said to have become saturated with respect to silver, hence the melting point of foil and along. All along this curve, two phases, solid lead and liquid melt are prevalent. Your F hash is equal to C minus P plus 1 is equal to 2 minus 2 plus 1 is equal to 1. Then the system is univariant. Eutectic point O. This is the point where two curves OA and BO meet. At this point, solid lead and solid silver are equilibrium with fused mud at the three phases present. Therefore, there are no degrees of freedom. As the only equation. The point O represents the lowest possible temperature. period below which a liquid cannot exist and above which the liquid phase cannot be enriched either component by freezing out the other component. Such a liquid mixture of two components G and PB which has the lowest freezing point compared to all of the liquid mixture is called eutectic point. This fixture makes a complete a constant temperature. No freezing gives two components a solid phase in a same proportion if they are present in liquid. The temperature corresponding to the eutectic point is called eutectic temperature. This is always lower than the melting point of the components constituting eutectic mixture. Let's talk a little bit about the partition process, dissociation and galena. PPN ore of lead is usually associated with silver. When galena is worked for the extraction of lead, some traces of silver pass into it. Because the silver is soluble and at some extent the lead thus obtained is called an Argentiniferous lead. The delivery organization can be solved with the Argentiniferous lead containing small percentage of silver in the first evaluated temperature well above its melting point. So the system consists only liquid represented by point allowed to cool gradually along the line XY without any change in concentration till the point Y is reached. As soon this point is attained, lead starts separating. Solution contain progressive. Increasing amount of silver further cooling will shift the system along line YU that contains separator which can be removed with the help of perforated spoons and the melt continues to be richer and richer in silver till the point where it is where alloy containing about 2.4% silver is obtained. The above principle is employed in pattern which is used for increasing to relative proportion of silver in the lead. The relative increase in the amount of solid lead the sulfate also the silver in the melt cooling down.